Hello everyone. In this video we are going to explore a new topic that is cognitive radio. Cognitive radio. It is a form of wireless communication in which a transceiver can intelligently detect which communication channels are in use and which ones are not. Under this cognitive radio we are going to talk about the following topics. 1. History of cognitive radio. 2. Architecture. 3. Operation. 4. Types of cognitive radio. 5. Pros and cons of cognitive radio. 6. Comparison between traditional radio network and cognitive radio. History of cognitive radio. Concept of cognitive radio was proposed by Joseph Matola III in a seminar at KTH Royal Institute of Technology in Stockholm in 1988, published in an article by Matola and Gerald Q. Maguire Jr. in 1999. Cognitive radio enables maximum spectrum utilization efficiency through opportunistic access to temporarily unutilized portions of spectrum. Cognitive radio enable the usage of temporarily unused spectrum, referred to as spectrum hole or white space. Architecture of cognitive radio. A cognitive radio basically contains a software-defined radio as its hardware component. The principal components of the software-defined radio are the RF front end, a modem and a receiver transmitter chain. From a layered outlook, cognitive radio architecture can be described to consist of 1. Physical layer, 2. MAC layer, 3. Network layer, 4. Transport layer. 1. Physical layer. In the physical layer, spectrum sensing is the primary task, which includes functionalities such as detecting spectrum holes, opportunities over wide frequency spectrum. 2. MAC layer. In the MAC layer, a decision is taken on whether transmission should be carried out or not, considering that the spectrum sensing could be faulty and the process of utilizing the spectrum holes. 3. Network layer. The primary tasks at the network layer are constructing topology, addressing, and routing. The topology construction involves spectrum detection, neighbor discovery, and topology management. 4. Transport layer. The transport layer protocol is responsible for flow and congestion control, the performance of which is affected by MAC protocol performance and spectrum mobility. The throughput of the transmission control protocol is largely affected by the spectrum management techniques. SDR transceiver. In this we can see the front end of the receiver, in which the first block is the RF block or the radio frequency block. Next we have the ADC, that is an analog to digital converter. And the last block that we can see is a baseband processing signal. This block processes the baseband signals, so the received signal antenna receives the signal, and through all the blocks it is given to the user. Similarly, the user transmitted data goes in the reverse direction and is transmitted using the transmitter antenna. Now we'll just have a brief look at how the receiver looks like. Firstly, receiver filter will filter the signals that have been received. That is, it filters out the frequency band of the service from the other frequencies that are available. This signal is then given to the low noise amplifier, which basically will amplify the signal in such a way that it increases the SNR, or the signal to noise ratio. This signal is then transmitted or forwarded to the down converter. Remember, since this is an RF circuit, the signal here is in the range of radio frequencies, which is extremely high, whereas the baseband signal or the original information signal is of a low frequency. So this signal is then down converted using a down converter. Down converter has a local oscillator frequency which has been given, which is nothing but the carrier frequency. The down-converted signal or the baseband signal then moves on to the baseband filtering. This baseband filtering selects only that frequency on which the actual service is happening. It removes the effect of adjacent channel interference as well. This signal frequency is then passed through AGC, which is called as an automatic gain control. This automatic gain control amplifies or increases the amplitude of the signal in such a way that the signal can then be perfectly quantized and converted to a discrete signal. So automatic gain control signal is then given to the ADC circuit. This converts the analog signal into a discrete form of signal in terms of amplitude as well as time. Operation. Cognitive radio operates on a typical duty cycle that involves detecting spectrum idle space, selecting optimal frequency bands, coordinating spectrum access with other users, and vacating the frequency. The cognitive tasks can be distributed over four main cognitive functions, namely, spectrum sensing, spectrum management, spectrum mobility, and spectrum sharing. Spectrum sensing. On the startup of a cognitive radio device operation, the first task to be done is to get acquainted to the surrounding radio atmosphere by identifying the available spectrum opportunities for transmission. Spectrum sensing allows CR to detect spectrum idle space, which is an unused frequency band that can be utilized by secondary users, sus. When PUS, primary users, start using the licensed spectrum again, CR can detect their activity through sensing and vacate the frequency to avoid harmful interference. Spectrum management. After spectrum sensing stage, the CR device now has information about the available spectrum holes that would be spread over different frequency bands or time slots or locations or codes, etc. Spectrum management protocol has to analyze data given about spectrum from the sensing stage, and then decide which band to choose according to the COS requirements. Spectrum mobility. As soon as a primary user starts transmission over a channel occupied by a secondary user, the secondary user must immediately evacuate the channel in a smart and efficient manner that would not cause any harm to the integrity of the primary user transmission. Spectrum sharing. This technique involves sharing spectrum resources among multiple users, including both primary and sus. Cognitive radio devices can share spectrum resources by using techniques such as time division multiple access, TDMA, frequency division multiple access, FDMA, and code division multiple access, CDMA.
Types of cognitive radio. The two main types of CR, heterogeneous and spectrum sharing. In heterogeneous CR, operators run several radio access networks, RANs, using the same or different radio access technology, RAT, protocols. Heterogeneous cognitive radio uses a network-centric approach, and the frequency bands allocated to the various RANs are fixed. This approach allows for more flexibility, adaptability, and efficient spectrum utilization across a diverse range of applications. Spectrum CR. In spectrum sharing CR, several RANs share the same frequency band. They also coordinate with each other to use unoccupied subbands intelligently and optimally. Now we are going to talk about some pros and cons of cognitive radio. Pros of cognitive radio. It offers better spectrum utilization and efficiency. It improves link reliability. It is lower in cost. It uses advanced network topologies. It has simple network architecture. It is easy in configuration and easy to upgrade. It is less in complexity. Improves satellite communications. Improves quality of service, COS. The cons of cognitive radio. There is no complete automation and it requires user intervention for any changes to be implemented. It always requires multi-band antenna. Quality of service, COS, in cognitive radio is affected due to its adverse effects. Translation of observations into actions is a big challenge in cognitive radio. Comparison between traditional radio network and cognitive radio. 1. Spectrum utilization. Traditional radio network. In a traditional radio network, spectrum allocation is fixed and rigid. Cognitive radio. It is designed to make more efficient use of the radio spectrum. It can sense its environment and adapt its transmission parameters and frequency to access underutilized spectrum. 2. Frequency allocation. Traditional radio network. In traditional radio networks, frequency allocation is typically managed by regulatory authorities. Cognitive radio. Cognitive radios have the ability to dynamically search for and access available spectrum, including licensed bands when they are not in use. 3. Interference management. Traditional radio network. In traditional radio networks, interference management is primarily handled through fixed frequency assignments and coordination. Cognitive radio. Cognitive radios are designed to actively avoid and mitigate interference. They can sense the spectrum, detect interference, and switch to cleaner frequencies or adjust their transmission parameters to reduce interference, thus improving overall network performance. 4. Network adaptability. Traditional radio network. Traditional networks have limited adaptability and are often static in their operation. Cognitive radio. Cognitive radio networks are highly adaptable. They can autonomously adjust their parameters and configurations in response to changing network conditions and spectrum availability. 5. Spectrum sharing. Traditional radio network. Spectrum sharing in traditional networks is often limited to specific frequency bands and is subject to regulatory constraints. Cognitive radio. Cognitive radios are designed to facilitate dynamic spectrum sharing, enabling multiple users to share the same frequency bands efficiently without causing harmful interference.